Hello everyone. Today we are going to explain wavelet transform method to remove the baseline vendor from an ECG signal. Here you can see this is a raw ECG signal in a black color first graph. The second one is approximation of the baseline component with the help of wavelet transform, and we subtract this approximation from the original raw signal and we get this a baseline subtracted and drift removed. If you want to read further about this wavelet transform method, here is a research paper published in IEEE conference, and the paper is about comparison between different wavelet transforms and the thresholding technique for ECG denoising a pure ECG signal and include a noise, and then they applied the DWT and the thresholding technique and then inverse DWT, and then they get a denoised ECG. So that say that Symlet and Denoising are found to be better than any other wavelet transform, and hence they are the best approximation for the ECG signal. Based on this conclusion, we are going to use this Symlet wavelet transforms to denoise over ECG signal in this tutorial. For the dataset, we can use the PhysioNet, but we are going to use, because we are going to demonstrate only on a single ECG signal, we are going to use a SciPy library, which provides an electrocardiogram dataset, and it is a part of the SciPy.datasets library, and the dataset is one-dimensional signal representing a 5-minute long ECG, which is sampled at 360 Hertz. So these are the core information we required about the SciPy dataset, and here you can see the signal length is 5 minutes and the sampling rate is 360 and the units is millivolts. This dataset is ideal for experimental with the signal processing techniques like filtering and Fourier transforms. So if we go to the official documentation of the SciPy library, here we can see that it is an ND array, the electrocardiogram in millivolts sampled at 360 Hertz. So if you want to see the references here, they fetch the MIT BIH arrhythmia database, and this data set is could be loaded with these two lines, and it could be plotted with the signal code. So if we fetch this code and we go to over Python IDE, and let's create a new file and paste this code here, and let's break down these things. We are importing the NumPy, matplotlib, and we are taking the FS signal and ECG.size. We did not fetch the ECG yet, so let's go back and first grab the ECG signal, which we can simply take from these two lines, and we can import these two lines here. So now we have the ECG from the SciPy dataset, and let's save this file inside my Python projects. So we save that, and now let's run this code and we will be able to see this plot. So here is a snapshot of the ECG signal. You can see a clear drift from the zero line. This is called a baseline vendor. And if you are not aware what a baseline vendor is, we can Google it, and the baseline vendor on ECG means that the straight line in between the spikes and waves is not so straight. So it can wiggle up and down you in a science direct, and baseline vendor refers to the low frequency fluctuations in an ECG signal that are not of cardiac origin, and it is typically below the 0.5 Hertz. So basically you can also use a Butterworth filter, which we done in our previous tutorial, where we removed the baseline vendor using a Butterworth filter. But the problem is that Butterworth sometimes introduce morphological changes in our original ECG signal. So what we do, we look for different techniques which keep the morphology of the ECG intact. One of these technique is an wavelet denoising technique, which we are discussing in this tutorial. and can distort the ECG waveform, especially during stress test or when there is a body movement. Body movement is a major involvement of disturbing the ECG signal, and different techniques like linear filtering and polynomial fitting are used to remove baseline vendor from ECG signals. So you can read these papers related to the baseline vendors if you want to know more about that. This is a simple ECG recording are usually contaminated by different types of noises and artifacts, and in the pre-processing step the goals are to reduce such noise and artifacts to determine the fiducial points like P, Q, R, S, and T, P onset, P peaks, P offset, QRS onset, QRS offset, T onset, T peaks, and T offsets. So these are the points which we are interested if we want to do some decision making on the ECG signal, and to avoid the amplitude and offset effects to compare signal from different patients. A typical type of noise are described briefly and grouped into following categories. Have a power line inference, which is a signal of frequency either 50 or 60 hertz and its bandwidth is below 1 hertz. And baseline vendor, which we are interested in today's tutorial, is a low frequency or normally 0.15 up to 0.3 hertz noise. This noise results from the patient inhaling or compels a baseline shift of the ECG signal. So, when we inhale, we move our body, and the body movement introduce noise, which is a baseline vendor noise. And there are all of these bunch of other noise, which we need to remove that. So let's see what a wavelet transform is. So basically a wavelet transform is a mathematical technique used to analyze signal by decomposing them into components of different frequencies. So this is a very important thing about a wavelet transform. It decomposes the signal into various form of, and unlike the Fourier transform, which provides only frequency information, the wavelet offers both time and frequency localization. So if we do a wavelet transform, unlike the Fourier transform, we'll get both information. The Fourier only gives the frequency information, but the wavelet offers both time and frequency localization, making them ideal for analyzing non-stationary signals. So this is an important point, that analyzing non-stationary signals where frequency content changes over time. So if we need to keep this relationship intact with non-stationary signals, if there is a stationary signals, we can go with the Fourier. But if the signal is non-stationary, the type of wavelet transforms, there is a discrete wavelet transform, the continuous wavelet transforms, and stationary wavelet transforms, as well as multi-resolutional analysis. The continuous provides a continuous mapping of the signal in a time and frequency. It computationally intensive but ideal for detailed signal analysis. On the other hand, the discrete use a discretized scales and translation, offering a compact representation of the signal. It is widely used in compression and denoising. So as you know that from the research paper, we are going to use the DWT. And the common used wavelets are Haar wavelet, which is the simplest wavelet suitable for detecting sudden changes. And if you are going to detect sudden changes in the signal, Haar wavelet is sometimes most obvious choice. And Derbyshire's wavelet are smooth and compact, widely used in compression and denoising. As we see in a research paper, this is also an ideal wavelet for ECG denoising as well. The Symlets, which we are going to explain in today's tutorial, is another obvious choice for symmetric version of Debye wavelets, reducing phase distortion. So because the phase distortion is a main point, so that's why we are going to use a Symlets with a soft thresholding techniques. And then we also have a Morlet wavelet, which combines a sinusoidal wave with a Gaussian window. It is ideal for time frequency analysis. So we are going to focus on this wavelet. So let's add some noise into our ECG signal. So we change this. Here is our full ECG. This is our full ECG. The sampling rate is 360, and we will getting a 4,000 samples. And then we are creating a time signal with the help of NumPy library, and we are getting a clean ECG with this that number of points. And after that, we are adding a noise of sine wave with the 2 pi of 0.3 multiplied by time plus 0.08 of amplitude of another random noise. So these two noise are added, and once is a sine noise which will considered as a baseline vendor, and second is a random noise which is, and here you can see a detailed sine wave and the noise added with the ECG signal. And here you can see clear shift from the zero baseline. And here we have a noisy signal which we are going to denoise using a wavelet transform. So first of all, we will create a Symlet 10 kind of wavelet. And after that, what we are going to do, we need to calculate a desired level. And we are simply doing this by dividing the fs with the cutoff frequency. And we need to define the cutoff frequency. And let's say if we say that 0.5 is over cutoff frequency, and this will compute over a desired level. And after that, we calculate the maximum levels, and we use the PyWT library which we need to import. We will do that later by importing PyWT, and then we are going to DWT maximum level. So we'll computing this, and we provide the n because n number of samples we are going to provide, and then PyWT wavelet. This will provide the kind of wavelet we are going to pass, and we provide a string of kind wavelet of Symlet 10, and then we will add a parameter of DEC underscore length. So this will compute the maximum levels, and after that we are going to estimate this level by getting a minimum number from desired level to maximum levels. So this is a maximum levels which are this kind of wavelet have for this number of points, and the desired level, this is a desired level. So if whatever the minimum value is, we are going to choose that as our desired level. So after that, we are going to calculate the coefficients of the wavelet, and we provide the ECG signal which is noisy ECG signal, and then we will provide the kind of wavelet which is Symlet 10. We provide this parameter as a string. Then we will provide the desired levels. This will compute that number of coefficients. And once we have the coefficients, we will calculate the approximations, and for that we will use this formula, and this will calculate the coefficients approximations. And once we have that, we will use the wave rect function of the PyWT to compute the coefficients. We use the wavelet DEC decomposition, and the wave recomposition is wavelet of recomposition. This is kind of a recomposition with the help of coefficient approximation and wavelets with n numbers. And once we have this baseline estimation, what we are going to do, we are simply going to subtract this baseline from our original ECG signal, and we will get the ECG wavelet baseline. Then now we simply added some plots to show the clean and contaminated signal with the initial comparison. After that, we are simply doing the same wavelet decomposition baseline, and then we decompose it to the coefficients, and then we reconstruct the coefficients, and then we plot the extracted baseline. And after that, we subtract the baseline to get the denoise signal, and we plot the denoise signal. So let's try to run this complete code and see our plots. And this is our clean ECG with the contaminated ECG. And you can see these noisy signals, and then what we are going to do, we contaminated ECG and the extracted baseline. As you can see, the baseline is properly approximated, and it is a proper approximation of the actual baseline rendered. So once we done that, we remove the signal, and here we have the original clean ECG, which is a blue one. Then we have contaminated ECG, and then we have a denoised ECG with the Symlet 10. You can see the green one ECG is purely on a zero line. So we have a pure denoised ECG with the help of baseline vendor remover with the help of Symlet 10 wavelets. So that's all for today's tutorial. If you have any questions, just leave a comment. If you want this code, contact me on a WhatsApp. Thank you.